So we're going to finish off this semester, and we're going to finish really off derivatives. We're going to change paces once we come back from the break to another different type of problem that calculus helps us solve. So this is the last lesson. We'll have a test, we review for the midterms, we have our midterms, we come back and we change gears. So I want to leave you with the most important lesson, and probably the number one thing I want you to take away from this class and what calculus can do for you is calculus helps you find maxes and mins of things easily. That's what it means to optimize, to find a max or a min. How does calculus help you find maxes and mins easily? Well, you know how to take a derivative and set it equal to 0. Is it in that room right now? No, they're not.
Yeah. Go look.
I'm not looking. No. Okay? That's the key. If I want to find a max of something, take the derivative, set it equal to 0. It could be anything. I have some sort of expression for it. I can take the derivative of that expression, set it equal to 0. It's great. Now remember finding relative maxes and mins. This is from Unit 4. We would take the derivative of this and set it equal to 0. That's how we start. We also need to kind of keep in mind when it's undefined, but it's not applicable in that many situations for the functions we're dealing with. So we get 0 and 2. All right, so these are possible maxes and mins. How do I determine if they are maxes or mins? Yeah, we use our number line to analyze the signs of our derivative, because the signs of our derivative tell us if a original function is increasing or decreasing. So we got positives, negatives, and positives. That's telling me that f is going up from left to right until it gets to 0. Then it goes down from left to right until it gets to 2. And then it goes up after 2. So that enables me to kind of sketch the general shape of f. We can go even further and plug in and find the function values using the original equation. You could say, oh, well, f of 0 is 5, so this is the point 0, 5. And f of 2, 8 minus 12 plus 4, this is actually at 1. So I didn't do a great job sketching it, but after checking some points, I could say, oh, that's the point 2, 1. Something like that, okay? So, great. Well, now we're going to talk about absolute extrema, okay? These were relative extrema. This is a relative max and a relative min. A relative max, relative min, those are local maxes and mins. So max and min for a little part of the function. Absolute extrema is an overall max or min. And let's look at an open interval. So let's look at like the entire function. Well, this function we can see the overall min value is right here. That'd be the absolute min. The overall max. This function has an overall max, so absolute max. But some functions do not have a max or a min. This function, since it's trending towards positive infinity and negative infinity, just like the function we looked at, does not have an absolute max or min. Okay, so on an open interval, we may not have absolute extrema. It might not exist, which is why we typically talk about extrema on closed intervals. So let's look at absolute extrema, and we'll talk about the extreme value theorem, and this is on a closed interval. Okay, so let's look at first the interval from, say, -2 to 3. So that would include this point here and this point here. And I would look in between and including those 2 points. Notice the brackets that I use for the closed interval, including -2 and 3. I could see that when x is -1, I have a max. When x is 2, I have a min. That would be the absolute max and min on the closed interval. The function, if you look at the open interval, just the entire function, it doesn't have a max or min. But on closed interval, at these locations of the relative max and the relative min, those are the absolute maxes and min. But let's look at a different interval. Let's look at from -2 to 1. So that would include this point and include this point. Now think about overall maxes and mins. It's just the largest y value we could have or the smallest y value. We should notice that in this situation that the absolute max is still at x equals -1. But we don't have like a relative min on this function on this kind of curve. Instead, we have an endpoint here, which ends up being the minimum value. The difference between this point and all of the other points is that this is at an endpoint. If I looked at any other interval on my graph, no matter where I would look, I could look, say, from 0 to 2 or 0 to 1.5. Here. Well, the absolute max would be one endpoint. The absolute min would be the other endpoint. If I looked from 0 to 3, the absolute max would be this first endpoint. The absolute min would be there. All we are saying, and this is the extreme value theorem, on a closed interval, you are guaranteed, on a closed interval, you are guaranteed to have an absolute max and min either at the location of a relative max or a min or an endpoint. Okay? On a closed interval, and this is the extreme value theorem, you are guaranteed to have an absolute max or min either at a relative max or min or at an endpoint. Okay? Well, knowing that, we have something that we could call a candidates test. You'll have to write that in. You're asked to find an absolute extrema on an interval. Well, you're going to first start by setting your derivative equal to 0. This is the key to this lesson and the key to derivatives, really. Makes finding maxes and mins easy. But after you find when your derivative is equal to 0, you have possible locations of relative maxes and mins. All you need to do is compare those y values to the y values of your endpoints, and the largest one is your absolute max guaranteed, and your smallest one is your absolute min guaranteed. Okay? Let me show you what I mean by that. Find the absolute extrema of the function between 1 and 4. Change it up to 4. All right, so I have a closed interval. That means I'm guaranteed to have an absolute max and an absolute min. All right, well, step 1, set the derivative equal to 0. We already did this. Boom. And you get 0 and 2, however, your interval's from 1 to 4. So since your interval's from 1 to 4, you're only going to care about 2. Now, without having to do an analysis of whether or not we have a max or a min at 2, I can do my candidates test. I can say, hey, what are the y values when x is 1, when x is 2, and when x is 4? I am guaranteed to have an absolute max and min out of 2 out of those 3 candidates. How do I find those y values? You plug it into the original function. One minus 3 plus 5, that's 3. 8 minus 12 plus 5, that's 1. But man, I got to plug in 4. 4 cubed minus 3 times 4 squared plus 5. Ugh. This is kind of where the candidates test is not easy to work with. If I have to do a lot of arithmetic. If I had a calculator, sure, I could do that. But, you know, this is kind of key for not having a calculator and doing things quickly. So, I don't know, I'll just do it. 4 cubed in my calculator, just for brevity's sake. 3 times 4 squared plus 5. I get 21. Okay, but that took me a while, but at least I know definitively now doing this candidates test, at this point 2, 1, that's going to be the absolute min of my function on this interval, and this 21 is the absolute max. And if you're asked to find both the maxes and the mins, yes, do the candidates test, you'll find it. But if the question was just, hey, find the absolute min, we could probably do some analysis to not have to check all these y values and to make things, you know, a little bit easier and to kind of eliminate some of my candidates from my candidates test. And this is kind of also what we would do if we are not given an interval. Okay? We could always check the signs of our derivative to eliminate potential candidates. Okay? Let me show you. If I just asked you for, great, the absolute min. Well, instead of going straight to this, I'm going to do a little bit extra work before checking candidates. I'm going to do this number line analysis that I've done before, that I'm comfortable with. But instead of focusing at 0 and 2, I have a closed interval I will use that closed interval as my starting point and my ending point. This is a little bit different than what we've done. We've typically looked at from like negative infinity to our first point, and then from our second point to infinity or whatever. And I have this value 2 in between. Well, I can analyze the signs of f prime and realize that they're negative between 1 and 2, and they're positive from 2 to 4, just by using a test point and knowing that you're either positive or negative between zeros. Well, through this analysis, you know that you're starting at a location, you're going down until you get to your location at 2, and then you're going up from there. Because of that, I do not have to check my endpoints. I can say definitively that x equals 2 must be the absolute min, the location of the absolute min. Now, this also helps if you are asked to find the absolute max, because if you're asked to find the absolute max, you could say, well, it's definitely not at 2, but it could be at 1 and 4. So at least you don't have to check 3 candidates. You can just compare 1 and 4 and say that's the absolute max at 4. Okay? So keep that in mind when you're analyzing things and finding absolute max and mins. Let's find some absolute max and mins of other things. Now, here is a question. We have a particle that has a position function given by this x of t. We're talking about t greater than or equal to 0. What is the particle furthest to the left on the interval from 0 to 2? Now, I'm not telling you, hey, find the max of this or find the min of this. You have to determine what you're trying to find the max or min of. Okay? Please discuss with your neighbors what you think you need to find and then how you would find it. Ready, set, go. The max of what? The min of what? What are you trying to find? Here's a ball. It has a position. When is it furthest to the left? It's when its position is at a minimum. That's the first thing I wanted you guys to figure out. Position is a min. So min of position or min position is a min. I'm going to say min of position. How do you find a minimum of your position? Ms. Gladich.
Can you visually show how being furthest to the left means a minimum?
I thought I just did that.
No, but on a graph, it's not a straight line graph. It's the lowest numbers, you mean? So the lowest X.
Yeah.
Oh.
Right? So on a graph, if this is the graph of my position, like that or something like that, well, you would think about the position of this ball on a straight line, because we're talking about something just moving to the right, to the left. These values would be positive values. You would say that this is a 0 here, so you'd have a positive position to a 0 to a negative position to a 0 to a positive back to a 0. That's how the ball would move if this is the graph of position. So when is your particle furthest to the left? It's when your position is at a min. That would be furthest to the left. Okay, good question. Hope that helped. So min of position. How do I find a min of position? Everybody flip back to the first page of this lesson's notes. And in the top right corner, what did you write? Take the derivative and set it equal to 0. It's that simple. If you want to optimize something, take the derivative. And I don't care that the derivative of position is velocity. I don't care that you know that. If you didn't know that, you could still answer this question. You could say, oh, I could find the min. I'm just going to take the derivative and set it equal to 0. I'm going to factor to solve. And I get some candidates. 0 and 1, both of them are in my interval, and I'm also going to look at 2. Now, if I wanted to do a lot of arithmetic, I would do my candidates test. And I'd say, okay, let's find and compare my position. Now, notice that I'm comparing my position. This is my y value. This would be going into this function, not into my derivative. My candidates test does not test, derivative values, instantaneous rate of changes. It compares y values, which are, the function values are the actual positions. Now, you could do that, or before I do that, let's look at the signs of f prime. Let's start at 0. Let's go to 2. In between at 1, we have a critical point. I see that if I plugged in a half, I'd get a negative x prime value. If I plugged in 1.5, I'd get a positive x prime value. That means my particle is moving to the left, then moving to the right, or its position is decreasing, and then its position is increasing, which means I'm definitely furthest to the left at 1. I don't have to do my candidates test if I don't want to. I can just confirm here, plug in 1, 2 minus 3 plus 2 is negative 1 plus 2, which is 1. If I checked and compared the other ones, I would also see that 1 is the least amount. If I plugged in 2, I'd get 16 minus 12, which is 4, plus 2, which is 6. It's probably pretty quick for you to do the candidates test. Now, where do I get these values, 2, 1, and 6? Again, I get them from my y values, okay? It's quick to do that candidates test, but, save some time and do a quick analysis of your derivatives. All right? So, next question. Same as the question above. We're given a position function. It's important to know that, yes, for now, for this next question, you need to know that the derivative of position is your velocity. Okay, so we now have a velocity function. So I'm asking you, when is the particle moving fastest to the left from 0 to 2? Actually, your question should be to the right. I believe in your notes it says right. So when is the particle moving fastest to the right from 0 to 2? Please discuss with your neighbors what you'd find the max of or the min of. Now, typically students answer this correctly, but they're a little bit more kind of complicated in your explanation and your answer. When I'm asking you, when is the particle moving fastest to the right, what I want you guys to think of is I want to find a max of velocity. Okay? I'm not talking about derivatives. I'm not talking about anything. I'm just saying, okay, when am I moving fastest to the right? When is my velocity the greatest value? And then I say, how do I find a max velocity? Well, I know that velocity is 6t squared minus 6t. I found that from the previous question. And when I took the derivative, I got the velocity function. How do I find a max velocity? Take the derivative, set it equal to 0. Notice I did not write A. I did not talk about second derivatives. I did not talk about any of that because it's maybe a little bit more complicated. You might confuse yourself if you're doing that. Instead, you say, I want to find a max of velocity. Take the derivative of velocity, set it equal to 0. Go. Find the max velocity on the interval from 0 to 2. Check your answers with a neighbor. And I would like you to find the max velocity. Not only when is the particle moving the fastest to the right, but what is the max velocity? Check with your neighbors. Now, it's important, after you do your analysis, you eliminate the candidate of 1/2. That's gone because you know that's going to be the min velocity. The possible maxes are going to be at the endpoint 0 or 2. We don't know which one it's going to be, though. It could be either, so it's important to check. Now, what are you checking? Not the prime values, but the values, the y values, the function values. The velocity at time 0 is 0. The velocity at time 2 is 24 minus 12, which is 12. So that's your max velocity on your interval there. Questions about that? Okay, let's see what else we can solve using this magical derivative set equal to 0, beautiful thing that comes from calculus. Here we go. I have two functions, 9 minus x squared and x squared minus 8x. They have a vertical distance between them at each x value. And I want to figure out when is the vertical distance between the two functions the greatest on the interval from 0 to 4. All right, so let's kind of sketch what's going on. That way we have a good better understanding of things. If I plug in 4, I get 16. I'm going to have 9 minus x squared is going to look like that. And then x squared minus 8x is going to have x-intercepts at 0 and 8. So they're probably going to maybe look like this, where this is my top function f, and this ends up being a bottom function g. We are told that at every x value, there is a vertical distance between the two. Now, we want to find the max distance, or d. So you're immediately thinking, okay, I'm going to take the derivative of my distance and set it equal to 0. That's what you should be thinking. It's that simple. But you just need an expression for d. Once you have an expression for d, you can set the derivative equal to 0. Okay. Now, what would be an expression for this distance here? Let me first start with, maybe a specific example. Let's say, and of course this d can be placed anywhere. So, this is a specific example, but the distance isn't always going to be this. Let's say this y-coordinate was 3 and this y-coordinate was -2. What would you say the distance was? 5, right? People usually can get that correct, but it's like, how do you calculate that? And then maybe I'll use two different functions like this and have this d right here and say this is 4 and this is 1. Discuss with your neighbors how you calculate the distance between two curves, the vertical distance between two curves. You would just subtract the bottom function from the top function. So the distance, or d, between the two functions, the expression for it would be 9 minus x squared minus x squared minus 8x. Okay, I'm going to take the derivative of that and set it equal to 0, and I'll be able to find the max distance. It's that simple. Now, maybe before I do that, let's simplify it a little bit. Distance is equal to 9 minus 2x squared plus 8x. When I take the derivative, I'm just going to say this is distance prime, the instantaneous rate of change of my distance. When that's 0, I'm going to go from, a positive instantaneous rate of change to a negative instantaneous rate of change, which means my distance goes from increasing to decreasing. I'm going to have a max. Or I might have a min. Let's just find out. So I take the derivative, I get negative 4x plus 8. I set that equal to 0. I can solve that very, very quickly and easily. X equals 2. I'm going to go ahead and assume that when x is 2, that's going to be my max distance. And that would be a correct assumption, but I should probably check this d prime around 2 from 0 to 4. Maybe it's at an endpoint. I plug in 1, I get a positive. I plug in 3, I get a negative. This must be the max. So no, I do not have to check my endpoints. It's important to check your endpoints, though, if you do not do your analysis like this. Okay, that's always a possible answer. So we just found that when x is 2, these two functions will be furthest away from each other vertically using calculus. Another great type of question where we can use calculus to answer a seemingly very difficult question. I want to figure out which point on the graph of root x is closest to the point 4, 0. What does that look like? Let's kind of graph what it looks like. We have the function root x. Ugh. And the point 4, 0. Okay. I'm trying to figure out which point on root x will be closer than any other point 4, 0. Mr. Besser. Yeah. All right, so it seems like a very, very tough question. It's like, man, which point do we think is closest to that point 4, 0? Well, we're trying to minimize, not maximize like the other situation, minimize the distance. But this distance isn't a vertical distance. This is a diagonal distance, potentially. So I can't use the whole like top minus bottom in this situation. We're talking about a specific point, and any single point, we have this diagonal distance. How do I find an expression for the distance between these 2 points, this and this? Discuss with your neighbors. Distance between 2 points. Any ideas? Yes, the distance formula is correct. Where does the distance formula come from? It comes from making a right triangle, okay? Where this is, you know, an a squared, this is a b squared, this is a c squared. We're going to call this d, though, okay? And we say that this distance squared is equal to the horizontal distance squared. Let me change that to an a here. Plus the vertical distance squared. And that's it, okay? Well, where does this distance formula come from that you know and you love? It comes from the fact that we need to find what this A is and what this B is. Well, this A distance is just the difference between your two x values. The x value here minus the x value here, I'll get this distance. Now, I don't care which way it goes because I'm going to be squaring it, but I need to kind of figure out what point this is at. And you might think this is a random xy, but it's not. It's a very specific point. It's an x where the y coordinate is the root of x. Based on the function, we say, okay, this is a specific x root x point. This is the most important part of the question, is establishing that point on the function. Okay, and this A distance is the difference between my two x's. This x minus this x will give me this distance here. The B distance is the difference between my y's. So that'd be the root x minus the 0 being squared. If you are comfortable with this, great. If you are not comfortable with this, remember that the distance formula is the square root of x2 minus x1 squared plus y2 minus y1 squared, which is just the Pythagorean theorem. I'm not going to go to d equals. I'm not going to take the square root of both sides because turns out minimizing distance squared is going to give me the same result as minimizing distance. Okay? So I'm actually going to leave this, and I'm going to find the min of my distance squared. Because if I had the square roots, the derivative would be a lot more complicated and I'd have to use the chain rule, and I don't want to do that. Questions so far?
Are we only going to be seeing this problem with the square root of x? Or
No.
if it's any function at all, it has to be
Yep.
x and a function of x?
Yes. Yes. And we'll do another one where it's something other than root x. Okay? Now, want to minimize distance squared? Take the derivative. I'm not going to write this derivative as 2d dx or whatever. I'm just going to say this derivative is d squared prime. And it's a regular d. It's not the special d. And I'm going to take the derivative of this. Now, I could take the derivative right away. I could simplify this first and then take the derivative. It's up to you. Probably I would want to simplify this right one The left one, I don't really care about simplifying. So that's just an x. And let's take the derivative now. Using the chain rule, I'd have 2x minus 4 to the first times 1. The derivative of x is 1. Set this equal to 0. I get 2x minus 8 plus 1 equals 0. 2x minus 7 equals 0. Turns out, when x is 3.5, and this point here is 3.5 comma root 3.5, that point will be closer to the point 40 than any other point on the entire graph of root x. We probably should check that's a minimum distance. You probably should be able to tell that, we are decreasing in our distance and then we'll increase in our distance if we look at the squared prime starting at 0 where the function starts, checking in on 7/2, plugging it into this simplified d squared prime, we can see a negative then a positive, confirming that this is a min. And it must be the absolute min. Notice I didn't give you an interval. I just said over the entire function of the root of x, where do I have the minimum distance? Well, this confirms that that's the minimal. Okay, let's do the same type of question, only now with the function x squared and the point 2 1/2. Which point on the graph of x squared is closest to the point 2 1/2? Well, a random point on the function would be an x comma y, which y is x squared. That is important. The squared distance between 2.5 and any random point on my function, the expression for that would be the difference in my x's squared plus the difference in my y's squared. Maybe you want to simplify that. Maybe you don't want to simplify that. It's up to you. I'm just going to take the derivative of this right away. Sweet. Thanks. And my distance square prime is going to be equal to 2x minus 2 to the first power times 1 using the chain rule. This guy with the chain rule would be 2x squared minus 1/2 to the first times 2x. I'm going to set this equal to 0. Now to solve this set equal to 0, we're going to have to distribute some stuff and simplify. Okay, questions? Well, this brings us to some specific type of optimizing questions. Okay, moving into the next types of questions. In optimization, we want to try to minimize maybe like the amount of material we use in making a building. We want to maximize the profit that we gain from something, okay? Optimization, very, very important in business, in, cost efficiency and stuff like that, okay? Now, I don't want you to type down or write down all of these steps to solve. I just want you to think of how you did the related rates problems. Most specifically, think about what is fixed and using what is fixed to simplify what you are trying to, in this case, optimize. What is fixed? Use that to simplify what you are optimizing. Let me show you. We want to find two positive numbers, xy, where xy is equal to 192 and x plus 3y is a minimum. This must be true between these two positive numbers. Their product must equal 192. This is what we call as fixed. We are trying to find a min of x plus 3y. This is what we are trying to optimize. So again, how am I going to find the max or min of this? I'm going to eventually take the derivative of this and set it equal to 0. But since I have two different variables, I don't want to take the derivative just yet. I want to simplify it so that I just have one variable and I can just take the derivative with respect to that one variable and then set that equal to 0. So what do I use? I'm going to use this fixed relationship. I'm going to solve for a variable. And sub into what I'm trying to optimize. Let's say we solve for x. X is equal to 192 over y. Take that, plug it in for x. I get 192 over y plus 3y now. I'm going to take the derivative of this with respect to whatever variable I have, in this case y. I'm going to just pretend they're all x's, kind of. That way I don't have to worry about any dy dx's or stuff like that. I'm just going to take the derivative and set it equal to 0. Now either using the quotient rule or rewriting this as 192y to the negative first, you can get that this derivative is negative 192 over y squared plus 3, that equals 0. Take that derivative, set it equal to 0. Solve. I'd get negative 192 is equal to negative 3y squared. Y squared is equal to 64. Y is equal to plus or minus 8. However, we are told in the problem that we are finding two positive numbers. So I'm going to use just a positive 8. So it turns out when y is positive 8, then I can use this already kind of fixed relationship to find x. 192 divided by 8 is 24. So it turns out when x is 24 and when y is 8, those two numbers that multiply to equal 192 will produce the minimum sum of the x plus 3 times the y. It ends up just being 48. If I pick any other two numbers that multiply to get 192, they will produce a larger x plus 3y. Okay? The second question, same deal. We want to maximize xy. Before I try to take the derivative of xy and set it equal to 0, I'm going to maybe solve for a variable. I'll solve for x. Then substitute it in for x. Now, in both of these situations, I have, y solved for and just y's, and that's fine. If you have x's, you can use x's. It's all up to you. Let's take the derivative of this with respect to y. Now, I'm not going to use the product rule. I am going to simplify this. And then take the derivative and set it equal to 0. I get 100 minus 4y. I'll get y is 25. If y is 25, x is going to be 50. That would produce a maximum product if the first plus 2 times the second has to equal 100. Guaranteed. They get a little bit more complicated if the fixed and the maximizing, the optimizing, or the optimizing equation expression is not given to you. Take this example of the gardener. A gardener wants to make a rectangular enclosure using the wall of a barn as one side of the enclosure and 120 meters of fence for the other 3 sides. It has to be a rectangular enclosure. Find the dimensions that give the greatest area. Well, it's a rectangle, so these two have to be the same and this has to be the same. You could obviously draw this in a different way and say like the y's are the same and you have one x. It doesn't matter. I just draw it this way, but there's multiple ways to do this problem and to set it up. Now, you have to create the fixed relationships and the expression for what you are trying to optimize. The constraint, the thing that is fixed, is that you have 120 meters of fencing for the 3 sides. That gives you that 2x plus y, that's got to equal 120. You want to maximize the area. The area is xy. This is what you're going to take the derivative of and set equal to 0. But don't take the derivative of xy. Instead, here it's easy to solve for y in this case. Y is equal to 100 minus 2x. Let's replace y with 120 minus 2x. Let's simplify that. Let's take the derivative of that with respect to x and set it equal to 0. 120 minus 4x is equal to 0. X will equal 30. Substitute back in. You'll get y is equal to 60. You'll find with these optimizing, like the answers that make a lot of sense usually are the ones that are correct. But obviously I want you to be able to get these answers. Yes? For area, I'm asking you to maximize the area. Yeah. I'm asking you to, like, here's the area, minimize the amount of material that you have to use to enclose that area. You'd have to minimize, like, the perimeter. Okay? Skip this one. I'll go back and do that on the video, but let's finish with this open box one. It's a very good question. You see this question often in calculus classes in college. We have a square sheet of material, 36 inches on each side. We are going to make a box out of this by cutting corners from the material, the corners being all equal sides, and kind of folding up these flaps. So these get cut out. Do we kind of see how the box is made? Now, we don't know how big this is, so we're going to denote the lengths of these square cuts as x. Okay? And I want to maximize the volume of the box. Okay? Well, the volume of a box is length times width times height. But I want a simpler expression just using one variable. So I need a length, a width, and height of the specific box. Well, we should see that this kind of length here is 36 minus 2x. And the width is going to be the exact same, 36 minus 2x. The height is just going to be x. I'm going to simplify that to be 36 minus 2x squared times x. Now I want to maximize this. So I'm going to take the derivative and set it equal to 0. I may want to simplify this first before I take the derivative. In this case, kind of like the 36 squared and the arithmetic is a little bit kind of crazy. So let's just take the derivative of it and use the product rule and the chain rule. So I have a product. So I have the derivative of the first. What I'd say is 36 minus 2x times negative 2 times x plus the derivative of x, which is 1 times 36 minus 2x squared. And I'm going to take that and set it equal to 0. Now, maybe distribute things to solve this, but actually I'm going to factor out the 36 minus 2x. And what I have left over is minus 4x plus 36 minus 2x equals 0. And I can go a step further and say this is minus 6x plus 36 times 36 minus 2x. This set equal to 0, we have a product. I'd get two solutions. When this piece equals 0, that's when x is 18. And when this piece equals 0, that's when x is 6. It appears I have two candidates, 6 and 18. Only one of these will make sense when thinking about producing a maximum volume. Discuss with your neighbors which one do you think is correct, the bigger number, 18, or the smaller number, 6? If you cut out squares 18 by 18, you are cutting out essentially the entire paper, which ends up producing a minimum volume because you really don't even have a box. But that's kind of the idea of that. That would produce a min. 6 would produce a max. You could also see that if you looked at the signs of V prime between 6 and 18, you would see that the volume would increase and then decrease. This is the max. This would be a min. Yes?
When you found the derivative of the volume,
yes.
Negative 2x, would it just be negative 2?
It is just negative 2, but then you have to multiply by the second piece. So this is the derivative of the first times the second piece. All right? I'm going to do the last problem while you guys are packing up for the video. Manufacturer wants to design an open box having a square base with a surface area of 108 square inches. Okay, so open box. See if I can draw my box. Square base. So we don't know if the height is the same as the base length. Surface area is 108 square inches. I want to maximize the volume. So surface area, I have one base and then 4 sides. And that has to equal 108. And we want to maximize the volume being x squared h, x times h. Okay, so appears this is tricky, but I'm going to solve for y, and it is going to be a little bit tricky, but I'm going to have 108 minus x squared over 4x.
like a job. It wasn't like a.
Okay, so I have this as y. I'm going to replace y with 108 minus x squared over 4x. I'm going to simplify this a little bit. It'll just be multiplying these guys by x. I have 108x. This would be x cubed. This is over 4, and this is over 4. And I'm ready to take the derivative, set it equal to 0. I get 108 over 4 minus 3x squared over 4. Set that equal to 0, solve for x. You can just do a couple quick calculations. You get x squared is equal to 108 divided by 3, which is 36. And that means x is going to be positive 6. Once you get that x, you can find y. Which is 3. Okay. So there you go. Optimization.